It's a marvelous thing. Now, I started last time on currents and circuits. Let's get a view here. The thing we're going to talk about now, which is your concern when you go into the lab, because you're going to be connecting things together. So let's go very, very briefly. What the idea is, we have some means of creating an electric field across circuit elements, and we push charge through these circuit elements. The first of these is the resistor, which is just sort of a clogged pipe, which is pushed by a battery, or I'm going to show you here today an electronic power supply, or what have you. This whole array of means of creating the so-called electromotive force to push the charges around in the circuit. And we think of that flow as a number of coulombs, charges, electrons, whatever, passing through the wire. Coulombs per second is called an ampere. And the ampere is common. You'll see it on a lot of appliances sometimes. There was the question, the point of the charge is not lost. If it enters a junction, it goes out the junction, and none is lost, none accumulates either. It just keeps flowing like water through a pipe. We had an example here. The thing I didn't get right when I was doing this, is the fact that there's some currents going this way, so that must mean there are 3 amps going this way, and gosh, this is going to be actually interesting. I'm going to explain why this trackpad works, and I'm going to try to defeat it somehow. I find that if I put it, let's see, where is the thingy? Maybe it's going to be a little less sensitive. We're going to explain why that is. Yeah, I'm going to beat this thing yet. Got it. Just with, let's see, lost him again. See, we're going to get into capacitors. These trackpads work by capacity, and the capacitor works on how distant things are from each other. It's kind of, the electric field goes from one to another, and you can get in the electric field and jiggle it around. So I think it's too sensitive for me. But, okay, let me go back here. Okay, in any case, in this particular case, if you follow the currents going into junctions and out of junctions, they are conserved. So let's just move on. And we made the point that we're dealing now with electricity flowing through materials, not through empty space. And so there is this resistance, which is caused by the fact that the electrons are trying to get through a material. The material is irregular, it's warm, so the atoms are jiggling around, and the electrons stagger through, and they are slowed down, and they go at constant speed. Even though there's an electric field, just like that ball going down the ramp through the nails, it ends up with a constant speed, which we explained in this picture here, showing that eventually, even though there's a voltage difference, a delta V across the resistor, there is a voltage, a potential difference, meaning there is an electric field, but this velocity of the charges ends up averaging to a constant speed because of the bumping that the charges have to go through to get through the resistor. And so you end up with Ohm's law, where the current is a constant current. If you have a constant voltage, you will have a constant current. The velocity will be constant, and it's just given by inversely as the resistance, right? The more pressure you put on, the more voltage, the greater the current will be, but the more resistance there is, the less the current will be. So that's Ohm's law. And the analogy to water is that it's like a clogged pipe, to some degree clogged. The more clogged, the more the resistance, and so on. The unit, again, for resistance is called, after Mr. Ohm. Sounds like a Buddhist chant, Om, but it's just a unit of resistance. And the current has its own unit too because it's used so much, and that is the ampere, or as we call amps. So now that's a very basic law that resistors obey, resistors. And they are symbolized by this jaggedy thing here at the bottom in your circuit diagram. Okay, but now we have to cut the question of, suppose you have more than, this is something we can understand, that if you have one, let's say you have a cell, a battery, even several cells, and you have a resistance, there's an electromotive force causing a potential drop across this circuit. The current will go from plus to minus. This is conventional current. Remember, that's the direction plus charges would go. In fact, what's really happening is that negative charges are going that way. So, but we call that a positive current. So we can get the actual current that flows in this circuit by just saying, well, there's a voltage drop across this V, which is the same as in this over R, if you know what R is, and you can get the current. Now, the rules are that if you go around a circuit, as much as the energy is built up by your EMF, it's used up by the elements in the circuit. So that whatever voltage is here, or EMF, you'll have a voltage drop across these. Now the question arises, what if you have several of them? And the configuration could be in various ways. We're only going to deal really with series and parallel connections. It could be more complicated, but I don't think we want to go with any. If in your lifetime you ever come across a more complicated thing than a series parallel circuit, you can stop and learn about it. I'm not going to bother you here with anything more complicated than that. But the point is, suppose I have, say in this case, here's my my set of resistors. Here I have a 2,000 ohm resistor and a 2,000 ohm resistor. Now the question is, what current will flow in a circuit like this? Oh, is this thing on already? Oh, that's the bad idea. Okay. Can you see that pretty well? Good. So in principle, if I close this, yes, something flows. These are 6-volt batteries. Oh, by the way, their connection is important. I think that, well, let me check what, they're 6 volts. Yes, it says on it 6 volts. I can check that just to be sure myself. You see, if you put the batteries in parallel, they will both have 6 volts, and there'll be 6 volts across both. You put them in series, they'll add up to 6 plus 6 is 12. So let me just see what, in fact, they really are. Oh, they're 12, so they're in series. Okay, that's good to know. So we're dealing with 12 volts. Okay, 12 volts. And so we have 2K here, 2,000, and 2,000. So the question is, what do we have? Do we have, in this case, you'll see how the lineup is in series. So in this case, the current has to go through this fellow and this fellow both. So the resistance actually is increased because he's got like two clogged pipes to go through. So actually the total is the sum of the two. 2 plus 2 is 4. Divide into 12. We see delta V is 12, and divide by 4, we should get something like 3 somethings. Okay, so let's just see. I'll close the thing. Hey, voila. Okay, roughly 3. I don't know how accurate these meters are, but that's the way it is. Okay, so that's nice. So we can say that if you have two clogged pipes in a row, two resistors in a row, we call that series. They're in a series. They add together just algebraically. That's the easy case. Now, funny things happen if you put resistors. Suppose, for example, I put another resistor in, but I put it over here. Now, you would think if I put another resistor in, things are going to get worse. The current's going to be blocked. That might be your first impression. But the tricky thing is, look where I'm putting it. I'm putting it across this one. I'm not putting it in series with it. I'm putting it across. So let's see what happens if I put it across. Let's see. So here's 3 amps. So even though I put an extra resistor in, my current jumped up. I've actually increased the current. I've made it easier for the current to flow, though I put a resistor in. That's the funny thing, in a way. I've just built up your intuition. The point is, I'm taking away a resistance, taking resistance out, but I'm actually sort of increasing the resistance. That's the thing you have to get straight in your head. And the reason really is, does anybody want to explain that? Yes?
Is one of the resistors like less resistant than the other, so they're splitting between the two resistors?
That's right. This one's 500 ohms. I don't know if you can see it back there. That's where you guys should come up closer. You can read the numbers. 500 ohms. Yeah, this is less. Moreover, it doesn't matter. If I give it another path, it makes it easier for the current to get through. That's the point. See, by putting it here, it can even avoid this 2K by going through another. So even if I put in 1,000, I'm giving it another path to go. The current should go up because it can go not only through here, it can go through here also. So actually making it easier for the current to flow by putting in more resistors. In this place, I put the resistance in, but putting it in parallel, I make it easier for the current to flow. So 2 resistors in parallel gives you less resistance than one alone. That makes sense. Like, for example, suppose you wanted to run out these doors. If you have one door open, there's a certain clogginess going through one door. But suppose I open the second door, it makes it easier to flow. So by opening doors or making paths, the more paths I have in parallel, the easier it is to flow. That makes sense now, right? Whereas if I had doors in a row, if I keep putting more doors and you're running down, that would make it harder to get through. So, yes, ma'am.
Even if they're like the same resistance level, like if they're both 2K, that still applies?
Yes. Whatever path, I could even make it more. I could even put in 4K. Let's try. Let's see if we have them here. Another 2K? No, I have a 2K. But even let me put in a 4K. So, but whatever it is, it's still another path. It's not as easy as the first one, but it's still a help. I mean, even if it's a narrow door, you'd rather go through. It makes it easy if opening a second door. So let's see. So you go from 3, and I'm giving it a kind of poor path, but a path. It does go. It is easier. Not so much, but easier. Right? Does that make sense? Still doesn't make sense.
No, is the amount that it goes up proportional to the difference?
Well, we'll do the math now. If you really want to do the math, you asked for it. Blame her, not me, okay? All right. Yeah, so now we have to do the math. Okay, let's turn off some of these. The math is not hard, by the way, but it is instructive, it turns out. And it uses some of the ideas we we had before. So I'm going to actually do both resistors and capacitors and compare them. So let me start with the resistor case here. And you remember we use Ohm's law for the resistor. So how did we write it? We had the current. Current is equal to the delta V, or V over R. Or we could write that in a number of different ways. By multiplying it across, you can have delta V. We may use any one of these, I equals IR. Or we could have R equals delta V over I. So there are lots of different ways of writing the same thing. Just so you can pick the one that's useful. Okay, now I'm going to say, let's try the series connection, which means that I have two resistors in a row. That's the first thing I did. Oh, hope I have a room enough on this board. That's the first one we had, where I had the resistor up here and the resistor up down here, just one of them, and they were basically in a row. The point is also that you can bend it with these wires, you can bend them around to do anything you want. The picture that we had before, I had the resistor up here, and then the wire was down here, and the battery was over here, and the ammeter was in here. That was the circuit, but I'm going to make it easier. I can put that up here. You can move these around to make it a little clearer for yourself. So this looks more like in series. And let's say it's R1 and R2. And the idea is we're going to, well, I guess I have to write it small. We want to try to find what is the equivalent resistance. Equivalent meaning that I want to have one resistor which is the same as these two in all respects. Namely, if I attach this to my battery, a certain current will flow, and there'll be a certain voltage across these two resistors, as far as the battery is concerned. So you want the same thing here. If I put that battery across an equivalent resistor, I should get the same current, and I get the same voltage across it. Now, the key thing in series that you have to know is that the current is the same through all the elements in series. That's the key clue. The current is the same in all the elements. Okay, well, okay. Mm-hmm. Okay, so if I want to find that equivalent resistor, I could say that the voltage across here is going to be the same as the EMF. Oh, that's another thing. You see, the other clue that you have to have is that the voltage is the same on a wire. I've said that before, but that's a very important idea. That if you have a very good conductor, its resistance is zero. If the resistance is zero, the voltage change on it is zero. So that means that these two have the same energy. You've lost nothing by passing current through here. That's an approximation. It's a good one in the case of circuits, small circuits. If you had a power line going miles and miles, that would be another story. But for these kinds of problems, we will make the approximation that this current does not produce any losses in the wires. So that means that there's no loss to here. The loss is all in the resistor, and then there's no loss to here. So that means that the energy is the same here as here, which means that the potential is the same. Okay. Then what you do is you just say that since this potential is equal to that, the potential drop across the whole thing is equal to the current in resistance 1 plus the current in resistance 2. And we use the idea that the current is the same to take out the current from that equation, and you just get that it's R1 plus R2. Now, the equivalent circuit, you want to say that the potential drop across your equivalent resistor is equal to the current times the resistance of the equivalent resistor. So when you look at, and the current, you're making the current the same, so that would say that the equivalent resistor has to be equal to this. So then you get the result that the equivalent resistor in series is equal to R1 plus R2. That's what we just saw experimentally, right? When I added this one plus that one, whatever it was, then it was 2 and, what did we get, 2 and 3, 4, 2 and 2? It was 4, we divided into 12, got 3. I think it was 2 and 2. So, anybody remember? No, okay. Whatever it was, we added this one plus that one, and we got, the sum was that. So that's the result that when you have resistors in series, they add. Now, by contrast, I guess I'll have to do it here. We'll do the things of resistors in parallel. That's obviously a little bit trickier. But in parallel, so the picture looks something like this. I have one resistor, R1, and I have another resistor, R2. That's like that little combination I had up here, right? And the question is, what is that equivalent to? Now, how is this going to act as far as the battery is concerned, or equivalent? So in other words, if I put a battery on here, there'll be a certain amount of current that flows, and there'll be a potential drop across these, and I want this one here to, if I put it across a battery, same battery, I want this one to act and give me the same current as the total here. In other words, the battery doesn't know the difference between having these two together or that one equivalent to it. So the clue, the main clue here, is that, you see, these resistors have the same potential here and here and here. So they have the potential of the battery, plus potential here. They have the negative potential here because of this wire carrying a constant potential. What we called it earlier equipotential surfaces. We may use that word. So in other words, in the case of the parallel circuits, the clue is that the V is the same on all the elements. That's the important thing when you come to parallel things, because the V is on this wire and it's on that wire, so it's the same across here as across here as across here. And because of this rule here, that the voltage is the same on a wire. Okay, so now we have to do this, and but what we also use the idea, though, now that the current splits the total current. I've got to get me a good piece of chalk. colored chalk is left. I total, that is not a good one either. Any better? Hope's better. The total current is equal to the current. See, what happens here is that you get some current flowing through this guy, I1, and that's the point. By putting in a second resistor, the current can also pass through I2. So that's why that's why the combination has less resistance, because they have two paths for the current to go. And so then you just have to say that the current through number 1 here, it feels the voltage drop of the E or V of the battery. But we're going to use this relation here. I is V over R. Oh, let's put a V, shall we say. V over R1, that's I1. And then we're going to have V, the same V because of that equal potential over R2. So that the total current is going to look like that. And I can, because V is the same on both, I can take it out in front, and I get V is 1 over R1 plus 1 over R2, like that. Okay. Now my equivalent circuit, on the other hand, I'm going to say that the total current is equal to the V, which is the same V, because it's the same battery, over my equivalent resistor. Right? So now if I compare these two equations, you see what this one says, this is V times 1 over R1 plus 1 over R2. Right? That's all that this means. It's a funny looking shape, but that's what it is. And this one is V times 1 over R equivalent. Now, if you look at these two, these are both the total current flowing. The same V, but here I'm multiplying by 1 over R equivalent, and here I'm multiplying by this thing, which says that 1 over R equivalent, these two things are equal, these in brackets. So it's equal to 1 over R1 plus 1 over R2. So that's the result for the parallel circuits. So I want you to understand the reasoning here. Yeah. And in my notes in the book, I give you, see, this is a very ugly, sort of ugly-looking thing, reciprocals of things. There is a more simple way of writing that. Just the arithmetic, you can write it actually, R equivalent. If you like to look at things right side up, you can do it this way. This is algebraically equivalent. So instead of doing reciprocals, if you want to find the equivalent resistance of two resistors in parallel, 1 and 2, you can just multiply them and then divide by the sum. And you can generalize this to any number, actually, on and on. For example, if you could have 3 resistors, and the result will be, you multiply this by R3, and then, but then you have to do something a little tricky down here. For 3 resistors, you have to do something like this, R1, R2, R3, and you have to multiply by divide by R1, R2, all the product combinations, R1, R3, plus R2, R3. So even if you're given 3 resistors in a row and you don't want to do all this reciprocal stuff, in other words, this generalizes also. If you have 3 in a row, you just add the reciprocal, and you would get the answer. But this is a way of doing it sort of, I find this a little bit more comfortable working with this kind of a thing. So that would be our equivalent for 3 resistors in parallel. Okay? That's just, you can check it. It's just algebra. Now, the only other thing that I wanted to make sure we covered on resistors, time is running again terribly fast. So you should also know about the energy loss. See, there's an energy loss in the resistor. See, it comes in with a certain amount of push from the battery. It has some potential here. And then when it comes out here, it has a lower potential. So it's lost some energy. The voltage, is the joules in a coulomb. Now, it's lost some voltage, so it's lost some joules. See, the current, but where did it go? Well, it went into bumping into the irregularities in the conductor. See, if those irregularities weren't there, and then you apply an electric field across here, the thing would speed up. But these things don't speed up. They go at constant speed, which means that they're giving that would-be kinetic energy into the heat of warming up the resistor. So a certain amount of joules for each coulomb is being delivered. So that, so the energy that is lost is equal to the voltage times the charge that passes through. In other words, it's the joules per coulomb times the number of coulombs. So each coulomb delivers a joule of energy if you have 1 volt. Now, in unit time, the energy delivered in time that is the physics word for that is power. That's the energy per unit time. So that would be dividing this thing by time, joules per coulomb times coulomb over time. And coulomb over time, we have called before, the number of coulombs that passes in unit time, is the current. That's the coulombs per second passing by, current. So the formula you have to know then is that the power delivered to a resistor is the joules per coulomb, which is volts, at times the current. That's the joules per coulomb, and this is the coulombs per second. It's joules per second. And that, because we use it a lot, is called a watt. I think this is the famous English inventor who invented the steam engine, James Watt. So this unit of power is in watts. And an appliance, for example, may be rated in watts, how many watts it uses, how much energy per second you use in an appliance. And your electric bills, that's another story. The energy, you see, that's power. But energy, again, is power times time. I just wrote it over here. So, and that's something I wanted to talk about, I probably won't get to right away, is so that's watts, it's power, times time. You'll see on your electric bills a unit, kilowatt hours. Kilowatts is thousands of watts, and the time that's convenient for electric use is hours. We often use seconds, but of course hours are just multiples of seconds. So that's a unit of energy. And I make the point in my notes of showing you my electric bill, where PG&E charges you. Well, let me see if I can find that. Where is it? Yeah. See, PG&E in the basement of the building, there is a meter, which when you use electricity, the meter turns and it counts the current going into your house. That's I. They know that they're giving you 120 volts. So you get I times V, and how much it so that the rate at which it turns is proportional to the current, and the amount that it turns is the total time that it's been turning. So that meter, the amount that it turns, is telling you the power, that's the voltage, times the current, the speed, times the time it's been turning. And that's how they measure how much energy they've delivered to your house. So PG&E says, we deliver energy, that's their slogan. They happen to be telling the truth in that particular instance. Not to disparage that they don't tell the truth all the time, but they do deliver energy, power times time. And your bill will be in kilowatt hours. It'll tell you power, kilowatt hours times time. In my notes, I go through a whole thing on how your house circuits are working. Check it out. It's nice. But let me see if I can go on to quickly. Trying to take your suggestion and move along. To capacitors. It's a slightly different game. Please look at this. If you're interested in understanding how the wiring is in your house, and also how to jumpstart a battery. That's a very useful thing to know, because let's say you have a dead battery. I'll just divert for a second here. Suppose you have a dead battery in your car, and somebody offers to give you a jump start. How should you connect it? Suppose this is plus, minus, and somebody comes along with a battery, plus, minus. How do you connect these? Anybody had that problem? See, that guy is dead, so he has no charge, and this guy has nice charge inside, voltage. Plus to plus, minus to minus, yes?
Plus to minus, minus to plus.
No. Good try. Anybody want to try something different? No, the reason is, look, this guy is dead. You want to put something in that's going to imitate what he wanted to do but can't do. So suppose I put him in like this. Now, he's dead. He's just out of the story. He's connected to your car, to your starter, whatever, but he can't provide anything. So the thing you want to do is provide what he didn't. So you want to connect this to this, because then you are connected to the starter the way the battery wanted to be. So you connect plus to plus, minus to minus. If you learn nothing else in this course, remember me when your car can't start. This is good to know. This is very nice to know. And to carry jumper cables, because you need the cable to go from this guy to there. So it's plus to plus. Because just think of it, I'm trying to replace the battery that's there and do its job. Does that make sense? Good. Okay, we have to now move on to this story here. Capacitors. Let's view it. Now, a capacitor is now the thing about the difference is this is another circuit element. I showed you you've seen what resistors look like. These are what capacitors look like. This is perhaps the most revealing thing. What it is two parallel plates. There's a plate and a plate, and let's see. In principle, you can vary the capacity by varying the amount of area that one plate has with respect to another, and it's the area, the facing area, that is interesting. So this is an exposed capacitor. It's our familiar thing. We've been talking about these parallel plates since almost the beginning of the course, and here's where it shines. So basically what it is, it's two plates. They don't have to be flat. In fact, you see a couple of cylindrical ones over there. But inside of them, there is just something like this, a positive and negative plate with equal charge, plus and minus here. The way you make it is, for example, we could take a battery and just put it on here. Now, again, this plate will achieve, because of the wire having the same potential, it's going to get plus, and this one is going to get minus. How does it do that? Well, the negative charges run out like this. This is physically what's happening. The negative charges run out because they want to get to the other side, and they feel there's a plus thing over here. So they run over here. If they do that, well, the negative guys, seeing these negatives coming, will run away down to here. Now, but unfortunately, they can't get across the gap because there's an empty space between these. There's air, say. This one here has air between them. So they can't get across. But what they'll do, they'll simply pile up till this side has a bunch of negatives on it, so much so that more negatives don't want to come. And this thing, if more negatives come, then whatever was chased away stays, and you have a charged capacitor. That's basically what happens. Just physically reasonable. Now, what capacitors are used for is for storing charge. The word capacity gives you a feeling for why you might get. So the capacitance of something like this would be the amount of charge that you store, depending on how much voltage you put over here. If you put on more voltage, you'll push the negatives away stronger. The capacity really tells you, I want to get a lot of charge for as little voltage as possible. That's capacity. And here's again our celebrated parallel plate capacitor. And you can calculate very simply. I won't do it for lack of time, but you should be able to do it using here Gauss's law to find the electric field. You want to find the voltage difference across the capacitor, which means integrating the electric field, blah, blah. You can do it right here. And so the feeling I want you to have for capacity is it's a storage of charge. And it's physical analog is a tank in which you might store water. A tank that has an area and it has a certain amount of volume up to a certain height, see? So the volume is equal to the area times the height. If you will, I won't do it today, but if you're interested, you could go through this analogy. The analogy is the area is the capacitance, the height is the voltage, and this is the charge, the volume that's in here. So that's the analogy to this. Because again, we could write C equals Q over V, or you could write Q equals CV. So the analogy is with the tank, the volume in there, the volume in here. I'm trying to avoid writing it looking like a voltage, but it's the volume is equal to the area. So that's the analogy here, and the voltage is like to the height of the water in the tank. And this is sort of the quantity of charge or the volume spilled. And actually, this works very nice. So you want to have the feeling I'm storing charge. And I showed you a few of these ones. And there's the analogy to the storage tank. Now, one of the interesting things here, just very quickly, one of the uses of these things is the fact that the capacitance of a plate like this is actually given by the area of the plate over the separation between them. That's derived in the book. Now, what's very cute is this device of a condenser microphone. What they do is you have a battery, and you have here's your capacitive microphone, and you see the amount of capacity depends on the spacing between. So if sound waves come in and they push, amazingly, a little bit on that plate and just push it in, the D changes. And so the capacitor changes. If you keep the voltage constant, the battery here, if you keep that constant, if V is constant and capacity is changing because I'm bringing the plates closer and further apart, then the charge on those plates will change. The charge will run, where is it? The charge will run through this resistor because there's a change, and then you pick up that and you can detect the motion of the thing. And that's a condenser or capacitive microphone. What time do we have? Yipes. Okay, let me quickly show you the other thing that, because the charge is stored there, the energy is stored there. So what happens now, I've turned on the power supply. This is a voltmeter, and the charge has to go onto these plates, and it doesn't go on all at once, because as the charge goes across, there's charge up here, so the next charge is an opposing field, and so it slowly builds up. The charge is going across the plates and building up on this between the two plates. And that takes time. It may take quite a few minutes. This is quite a lot of voltage. I put on, I'm asking for less than 2,000. This is going to make a loud bang, so I'm the closest to it. You may want to cover your ears. I'm up to 1,000 volts here. Now, I'm going to short the thing out. See, there are these plates attached across here. I have to turn this off. Now, I'm not charging it anymore. But you see the 1,000 volt is staying? Because I put the charge on the plates, and they are their own voltage source. Everybody's covered. Good, especially if you go to the concert this week. You want to have your ears working. Okay, now I come across here, and that energy is stored. Oh. It's real. Okay. And the voltage is back down to 0. So that's the way the world ends, with a bang, not a whimper. That's the way the lesson ends. Okay, so study up about capacitors. And next Friday, I think we can move on to magnets. Or maybe a little touch up. To do what?
Chapter 23.
On capacitors. We'll say a few words about capacitors, but we have to... and also it's pre-Valentine's Day, so we have a party. So my favorite gal will be there. Galileo!